All right, so we're going to talk about centripetal acceleration, but before we do that, we should probably talk about what it means to be centripetally versus tangentially oriented. So the way that I like to think about this is imagine that you are on the edge of the Earth, and we use this circle to represent the Earth, and when you're on top of the world, hooray, you have things like left, right, up, and down, and those all have a certain meaning. But when you are on the opposite side of the world, those meanings tend to be reversed, where up is down, down is up, left is right, right is left. So we need a better way of orienting what it means to be, up, down, left, and right for something that is constantly moving in a circle. So the orientation that we choose is the center of the circle itself. And we say that things are either pointing towards the center or away from the center. So that line, if you can imagine, is sometimes referred to as a radial line because it makes a radius with the position that you are interested in. So here we have this radial line, and if you were going to talk about what it meant to be centripetally or radially in, then that would mean pointing towards the center. So we call that centripetal, or sometimes we call that radially in, centripetal or center seeking. When it points in towards the center, we say that that is a positive orientation. And if it points away, so in this case, pointing away would point outside of the circle, we make that negative. So sometimes that's called centripetally or radially out, and we use negative for that. All right, now that can be used at any point on the circle. We'll say that in that case, centripetally in is positive and centripetally out becomes negative. The same thing here. Centripetally in is positive, centripetally out is negative. Now you might notice that this is an interesting choice because we normally like down to be negative and up to be positive, but we'll find that almost all of our problems, the centripetal forces and accelerations are pointing in towards the center, so we should just go ahead and choose positive for that orientation to simplify things. Now, along with the centripetal or center-seeking orientation, we get this other thing, which helps us understand what left and right is. So rather than talk about what left and right is, we talk about what is tangential to the circular path. Okay, so if you can imagine, there is a tangential, so like a line, a tangential axis that always helps us understand what left or right would be at any point on this circle. So the tangential axis that we use to orient things is going to have a different type of orientation. We don't say tangentially in or out. Instead, we talk about, in reference to the circle, whether the tangent that you're talking about is counterclockwise or clockwise. So counterclockwise is what we will use for positive orientations. So in this case, counterclockwise would look like that, and you would make these orientations positive. Clockwise is going to be negative. And again, on each of these, we can kind of get an idea of what it means to have a clockwise tangential direction. So for things that are moving in circles, it's helpful for us to think of a centripetal and a tangential axis rather than x and y, because the object is always rotating, and so saying things like up, down, left, and right on an x and y chart is not as useful as being able to orient things towards the center of the circle and then to talk about either clockwise or counterclockwise motions. Okay, so before we talk about centripetal acceleration, now that we know what centripetal and tangential means, let's talk real quick about how to add and subtract vectors so that you can understand how we derive centripetal acceleration. Basically, if you have two vectors, so let's say you have a vector here, we'll call it A, and then you have a vector here, we'll call it B. If you would like to add those vectors together, then you draw them head to tail. So here's A, here's B. Our vector addition, A plus B, looks like that. Now, if, however, you would like to subtract them, then what you would do is take A and add B, but in the opposite direction. So here's A, here's negative B. And what you get here is A minus B. Now, a quick shorthand way to recognize vector subtraction when the vectors have the same basis, meaning they start at the same point, like right here, is to realize that this difference between the two vectors is really just the line that fills in the gap. A minus B. Now, the reason why that's helpful is if we're talking about, let's say, positions that are different radiuses r away from somewhere, then this line right here becomes, let's say, r naught and r minus r naught, or your delta r, the change of your position. We're going to use this idea in our derivation for centripetal acceleration, which is happening right now. Okay, so for centripetal acceleration, let's imagine that you have another circle. We're just talking in lots of circles here, and you are at two different points on this circle. So let's say the first position that you're at is right here, where you have some radius r, that's your position vector, and later we'll keep the same radius, but say that maybe you're right here. Okay, now at each of those times, you are going to have a velocity that is tangent to the path, which means it makes a right angle with the radius and is tangent to the path like that. So that's your velocity at this point. And then here at this other point, you'll have the exact same tangential velocity. And let's say for the sake of argument that I can draw two lines that are the same size, because that's what you need to kind of indicate that they have the same velocity. Right, now in between these two positions is an angle theta. We're not actually going to use that angle, we're just going to mark it so that we can reference it later. Now, from this drawing, it's fairly clear to see that if we wanted to draw the displacement, which would be delta r, we do what we just did in the vector addition part. We draw a line that goes here to here, and we know that this new vector we've drawn is our change of position, delta r. Now, what's interesting about this is if I was to take both of these velocity vectors and draw them on their own, which is what I'm going to do, off to the side, and arrange them in a similar way to how the position vectors are, meaning they are joined at the tail. What's interesting about this is two things. First of all, I know that this angle right here is the same angle that's in between the two r vectors, the position vectors. That's because the velocity is 90 degrees from each of the positions. So basically all you've done is taken this triangle and rotated it 90 degrees, but with different length sides. Now the other thing that I can do is take a line and draw this here and get the change of velocity delta v. Now the reason why I've done this is because I have two triangles that are going to share the same interior angles, or sometimes we call those similar triangles. The thing about similar triangles is that the ratio of their sides are always equal. So this little symbol means therefore. Because these are similar triangles, therefore I can say that delta r divided by r is equal to delta v divided by v. So again, that's because these two triangles are similar triangles. They have the same internal angles, therefore the ratio of their sides is going to be equal. Now I'm going to use this relationship to get to an interesting place. First of all, I know that delta r over delta t, we'll do this off on the side, delta r over delta t, or the change of position over the change in time, is really just the velocity. And I can rearrange that so that I get delta r equals velocity times that change in time. And if I replace delta r here, with that, then what I get is v times delta t over r is equal to delta v over v. Now the next thing that I'm going to do is multiply both sides by v, so that what I get is v squared times delta t over r equals delta v. And then I'm going to divide both sides by delta t, so that I get v squared over r equals delta v over delta t. Now here's where you perhaps recognize something that's really important for us. Delta v over delta t is the acceleration of the object. So this tells me that v squared over r really is the acceleration of the thing that's going in a circle. Now, this acceleration is oriented so that it is always pointed centripetally in, meaning if I was to draw this centripetal acceleration for the object, say at this point, then that centripetal acceleration would look like this, and it would not affect any of the tangential velocity that it's at a right angle to. Meaning this velocity is not going to increase or decrease because none of the acceleration is actually in the same direction as it. Instead, this acceleration constantly changes the direction of the velocity instead of speeding it up or slowing it down. Now, to solve most of our problems, we are going to be using this equation for centripetal acceleration. To make things easy, we're going to go with the assumption that this velocity that the objects have is always constant. Now, when we do that, we get what's called uniform circular motion. So give yourself just a quick note on uniform circular motion. It just means that you will always have a constant linear, or sometimes we use the word tangential for that, velocity. Okay, so the velocity is always constant, which means that the motion of the circle that the object goes in, it has the same amount of time for each circular path. So if you know the radius of a circle, then you can always say that the velocity is going to be equal to the circumference, which is 2 pi r, divided by the amount of time that it takes for one circle. Now, sometimes we use the symbol capital T. T is sometimes known as the period, and it's the amount of time for one thing. For us, it is the time for one circumference, or just one circle. But knowing this equation can be very helpful for you. And again, this is only true if the velocity is the same at every point as the object is going in a circle. If that velocity is constant, then you can say what that velocity is just by knowing the radius and the amount of time it takes for one thing. All right, so let's use these ideas in some example problems. A toy car rounds a circular track that has a turning radius of 0.5 meter. The track makes up half of a circle, and the car completes the turn in 0.79 seconds. What is the centripetal acceleration of the car? Okay, so for this problem, you have a car that's going into a racetrack, and you know that the car, we'll do like kind of a top view, here's the car, is going to have some velocity, and then it goes into this track and makes a complete half circle. Such a great half circle. The radius of this circle is 0.5 meters. And you also know that it takes a certain amount of time to complete half of this, and that amount of time is 0.79 seconds. I'm going to call this lowercase t since it's not exactly the amount of time it takes for the whole thing. All right, now before, when we were talking about uniform circular motion, we were using the whole circle, but here we're only using half of the circle. So let's figure out how much time it takes to complete half of this circle. If the circumference of a whole circle is 2 pi r, then half of a circle is just half of 2 pi r. And if you don't know, half of 2 pi r is just pi r. Okay, so that's the distance that's traveled. I'm going to use d to represent that. So d is pi r. And if I want to find the velocity, I can just kind of do that raw distance over the time. And in this case, I have pi times the radius of 0.5 meters, and I'll divide that by 0.79 seconds. So when I put that in my calculator, I'm going to get 1.988. So let's just round that to 2.0 meters per second. So that is the tangential or the linear speed of the car as it goes around this curve. So to find the centripetal acceleration, all I need is that linear speed, square it, divided by the radius. So 2 meters per second squared divided by the radius of 0.79 seconds, or 4 divided by 0.79, and you get 5 meters per second squared, or 5.06 if you want to be a bit more precise. And sorry, I'm realizing now that that should be a meter, so that I get a meter squared over a second squared over a meter, which becomes a meter per second squared. Great. The next problem, you're driving a car in a circle. You have cruise control, meaning you have constant velocity, set to 35 meters per second, and you notice it takes 2 minutes to complete one circle. All right, so before we find the radius, let's figure out what that 2 minutes and the 35 meters per second, what that can tell you about completing one circle. So if it completes one circle, then you know your circumference is 2 pi r, and the amount of time that it takes to do that is 2 minutes, or we're going to say 120 seconds. That 120 seconds really is our period, or the amount of time it takes for one circle. So I can just kind of use my equation for uniform circular velocity, which is 2 pi r over the amount of time that it takes for one circle, and rearrange this to solve for what the radius will be. So to solve for the radius, I'm going to multiply both sides by t. So I get the velocity times t equals 2 pi r, and then I divide both sides by 2 pi. So I get r equals the velocity times the period over 2 pi, which is going to be 35 meters per second times 120 seconds over 2 times pi. And you put that in your calculator. Be careful that you divide by 2 times pi, but you put 2 times pi in parentheses. Otherwise, you'll divide everything by 2 and then multiply it all by pi, which is not what you want to do. So this gives you a large radius of 668.45. So let's just call that 668.5 meters, which is a large radius. This would be like a track with a diameter of almost a kilometer. All right. Now let's look at a small bug that is 10 centimeters from the center of a rotating record, experiencing a centripetal acceleration of 1.2 meters per second squared. The centripetal acceleration of the bug, if it's 15 centimeters from the center of the same record, is what we are looking to find. So let's kind of draw this situation. Here you have your rotating record. That's a terrible circle. There we go. And the bug originally is 10 centimeters. From the center. So he has a circle that has a circumference that depends on 10 centimeters per second. Now, you are told that the centripetal acceleration at this point, which again, the centripetal acceleration points in, the centripetal acceleration is 1.22 meters per second. We can write it like that, meters per second squared. And what we're going to do with that centripetal acceleration and a radius of 0.1 meters is we're going to figure out what the tangential velocity of the bug is. The tangential velocity of the bug depends on this equation, v squared over r. So to find v, we're just going to multiply both sides by r and then take the square root, or the radius times the centripetal acceleration. So in this case, that gives us 0.1 meters times 1.22 meters per second squared. And that gives you 0.349, but let's call that 5 meters per second. Now, the reason why we want the velocity of the bug is because we can actually figure out the amount of time it takes for one complete rotation. If we can figure out the time it takes for one complete rotation of the bug at 10 centimeters, then we know when the bug has moved to 15 centimeters, it will still take that exact same amount of time for one rotation because the whole platform rotates as one object. So let's find the time that it takes for one rotation. We're going to use the equation circumference divided by the amount of time for one circle, and all I'm going to do is divide that circumference by the velocity. Now, I know what r is. It's 0.1, and I just found the velocity, 0.35 meters per second. So when I do 2 times pi times 0.1 and divide that by the velocity, I get 1.795, so let's say 1.80 seconds. That's the amount of time it takes for one rotation. Now again, the object, the record, it rotates in a rigid manner, meaning that every piece rotates together. So if it takes 1.8 seconds for the bug to do a circle at 10 centimeters, it also takes 1.8 seconds for the bug to do a rotation at 15 centimeters. So all that changes in the second scenario is that you now are going to have a radius of 0.15. The time that it takes is still 1.8 seconds. Now, what we're going to do with this time in this radius is kind of work a little bit backwards from what we just did. We're going to find the new linear velocity of the bug at this point. The velocity of the bug at this point is, again, the circumference divided by the time, and we have a new circumference with our new radius. So 2 pi times 0.15 meters divided by the amount of time, 1.8 seconds. So 2 pi times 0.15 divided by 1.8 is going to give me a velocity of 0.5235, let's say 0.52 meters per second. All right, now we're close. With that linear velocity, I can find the centripetal acceleration by squaring it and dividing by the new radius, which in this case is going to be 0.52 meters per second, the whole thing squared, over the radius of 0.15 meters, which is 1.802, or we'll say 1.8 meters per second squared. So there you go. Great job.